Last video, we talked about some interesting things, at least they were interesting to me, about waves and how we can describe waves with a sine function. And now we're going to go into what happens inside a box where we have a point source that's sending all these waves out, sending all these waves out. When the waves bounce off the wall, they come back and they create what's called standing waves. So it's just as if the wave was just standing there. It's going back and forth, and the waves are just standing there. So what we want to do is figure out how many of those standing waves there are and what kind of frequencies go along with that. If we can plot the frequencies, then that's going to help us figure out what the energy is for each frequency. So there's going to be some math coming up, but I'll take it really slowly. And obviously, you can make comments, but I don't think anybody's watching these anyway, so that really won't make a whole bunch of difference. So I'll next go to my little drawing pad and we'll try to come up with some equations that try to make some sense out of that. Here's the board that we had last time. And it seems like, well, we got this box here, so we can talk about that. Here's the point source of the box. Let's see if I can make the cursor show up here. Here's the point source of it's right here. Here's the point source of the radiation. Here's the radiation going out, and it bounces off these walls and creates these standing waves that I was talking about. So we ended up with this equation, and we had this k, which was 2 pi over a lambda, which was the frequency. So let's back off here a little bit and just start talking about the waves that are going to occur from this thing. All right, let's see. We have to look at, let me get this, get rid of a bunch of this stuff. Okay, burning up time here. You sing a little song while we're erasing the board. And I'll leave that V equals L cubed down there because that's the size of that. And let's see, let's talk about standing waves that are going to occur. What I'm going to do first is pick the dimension. Oh, let's see, I got to get my marker working. There we go. Pick the dimension of the box. Here's L. And the lowest frequency that we can create as a standing wave is between these 2 points, and it's only half a wavelength. So these sides stay the same. These sides wiggle back and forth between the amplitude. Let's pick another one. Here's one where we get a full wavelength. And then you can draw it back this way because it's jumping back and forth between these. But this node here stays the same. And we'll do one more if my artistry can help me get through it. Goes up, down, up again. And let's see, did I get, let's see, 1, 2, yeah, and then it ends up here. And so we've got these 3 nodes. Okay. So what's the wavelength? Well, the wavelength is, in this case, let's see, did I do that right? Let me get rid of that. That's a little bit junky here. Let's put the wavelength down here, and that equals, what's the wavelength? Well, this is only half the wavelength, so the total wavelength here is 2 times the big L, dimension of the box. So it actually takes it, we're only looking at half a wavelength. Down here, what are we looking at? Well, the wavelength is exactly equal to L. And this last one's a little tricky. So this wavelength is actually, well, if it's like 2/3. Let's see if that makes sense. Here's the wavelength equals 2L over 3. Those are 3 of the frequencies that we can come up with. Now, how do we make this into a more general looking thing? Well, let's see here. What do we want to do? I think what we want to do is look at K equal to 2 pi over the wavelength. And now let's see if we can plug the wavelength stuff in here. If I plug in the first one, then that would be 2L for the wavelength. So that would come up looking like this. Pi over L. See how I put the 2L down here? The 2's cancel out. Then I've got an L. So this would be the first. Let's call this number 1. Number 2 wavelength is, what is that? That is, we plug in the wavelength down here. All we get is L. So that's going to be 2 pi over L. Then we plug in this last one, the third harmonic of the fundamental, and what do we get? Well, let's see what we get here. We've got we plug in a 2 over 3. Well, the 2's are going to cancel, and this 3, which is in the denominator down here, comes up, and it looks like 3 pi over L. So what's a general expression for this whole thing? Let me get rid of some of this stuff up here. My drawing board's not that big, so let's just get rid of some of this. Got to have a little music while you're erasing the board. So what's a general expression out of all this stuff? A general expression is all of the k's, which are all the different constants, are going to be n pi over L, where n equals all the natural numbers, 1, 2, 3, 4, ... So that gives us all the different frequencies that can occur there. Does that make any sense? Well, we're going to plug this into some formulas, and hopefully it will make some sense. So we want to remember this L3 that'll come into place here. Where are we headed with this? Where are we headed? What we want to do is come up with the frequencies that are all going to occur. Well, K is dependent upon wavelength. Remember, K was 2 pi over wavelength. So now we've replaced that wavelength with an L and all the different wavelengths that are going to occur with that. So does that get us partway down the line? Maybe so. Let me talk about a more general concept of what's going on here. If this was this arrow that's coming out over down here, this arrow that's showing up that I'm kind of drawing in there a little bit sharper. If you think of that arrow, the wavelengths are going all the way around. So really, there's a big sphere around this thing, a big sphere, and it's stretching out in all directions, stretching out this way, stretching out that way, stretching out that way, and it's actually stretching out in the third dimension that we can't really draw here because it's two-dimensional. So what would be handy here would be to know what the area, the surface area of a sphere. Surface area of a sphere. This will be helpful for us to, it helps if I can spell it right. Here, let me get, you make mistakes, takes longer, doesn't it? Okay. It's supposed to be an H there. Area of sphere is, what is that? Does anybody know? Does anybody know in here? What's this? What's the area of a circle? Area of a circle is pi r squared. Area of a sphere is 4 pi r squared. Now, what are we going to use as our r? Instead of an r, well, let's see, the r could be the radius of this sphere down here. So what about the r? What are we going to let this r stand for? Well, here's what I'm going to do is the r is made up of x direction, y direction, and z direction. So what I'm going to do is come up with a radical idea here, is that that r squared that I'm going to be involving here is equal to k in the x direction squared plus k in the y direction squared plus k in the z direction. Now, each one of these k's is like down here, it's going to follow this little formula 1, 2, 3, 4, and each one of these is going to have a different index for that. So this r squared is going to be involved in finding, we're going to use this area of the sphere, and as that area of the sphere gets a little larger, as those waves come out, there's different modes of frequency that can occur. So let's see what we've got here. We've got this stuff, and we're going to have to go on to another one. Let me stop and think about this for a little bit.